Good morning, everybody, and thank you for yesterday. I thought I should say a little bit more about USN IMERS. So although the Vice Dean for the Faculty of Technology told you all that USN IMERS was just the best, which we of course agree with, and that's why we have this dancing VR people here. But we have both a web page with information about what we do and all the people involved. We got another PhD fellow here, which haven't been named, which is Chrissy, and you'll meet her next time you come. USN IMERS has an overall aim to contribute to what should I say, greater usage of extended reality technology in many different ways. But it's all from the learning and training perspective and from the user side for being able to utilize it. So this is our grand idea, our grand figure of the things we are working on a sort of both a basic and applied level. So why are we so interested in extended reality technologies and virtual reality technologies? And that is, of course, because when you can use it, when you can learn in it, when you can experience culture in it, it's fantastic. And part of that is related to this fact that you believe that you are in a real reality. That's your experience. And the experience of being as if it was a real reality makes something to you, does something to you, enhancing learning and training. And Jeremy Bailenson has written a book about it. And one of the things he says is that we understand it not as a media experience, but as an actual experience. And yesterday, it was talked about that content is queen, right? Yes. Not only king. And of course, content is really, really important. And it's kind of the main thing as we move forward. How do we make content? And what is it for? And some factors that are really important is to understand the nature of the task that you want to move from a real world into an extended reality world. But another factor that's really important is to understand the user. So yesterday we heard about some fantastic content made for astronauts, made for surgeons. But you know, astronauts and surgeons aren't common people. They're kind of perfect. That's why they are where they are. The rest of us, we're common people. Common people have many different kinds of problems. And at the moment, content isn't necessarily made for those of us who are common, those of us who have common problems. And this is where USN IMERS comes in, because we see this technology. Why, when it's so fantastic, should it only be available for astronauts and surgeons? Why shouldn't it be available for every single person walking on this earth? And the other things that comes in is, you know, when you think about what you are going to use it for. Because when we heard from Signo Vivo yesterday, they already use this kind of technology for people who are deaf and blind. And of course, there are uses for that even with the headsets today. So this knowing what you want to do is really, really important. But if you want to do a performance task, and learning and training of professionals, of youths, of children, is typically performance tasks. And then there are different sets of criteria that are important. Another thing that always comes up is how authentic is the situation or the content or what you're doing in XR, and realism. And yesterday we heard about someone explaining to us how incredibly important it was that some of the content looks real. But one of the things we probably fear is that the more real it is, the more information there is visually, the more likely are we to exclude someone, if those things are the important bit of the content. So we also have to think about what other types of realisms can we use. And for Tori isn't here today, but one of the things we talk with her about, she's working in pedagogy, I'm really bad at saying that, is that maybe the visuals isn't so important. Maybe that can be cartoonish. But the actual roles played out, the actual language used, the actual situations using, when you're talking, is really important that it's real. And maybe it's more important. And if that's the case, we can go down on realism on the visuals, but go up on the realism on the audio. But some people also have hearing problems. So there are many, many different things. On this slide, I have lots of keywords that are important, because another factor that comes in is preconditioning. It's possible that when we're doing learning and training in VR or XR, the most important factor before we go in doing that task is preconditioning, doing something in the real world first. We're going to talk about some of these things today, but you see that I also put computational cost in red, because when content, hardware is getting cheaper and cheaper and better, content might be really expensive in developing, but there is also a computational cost for what you want to do. And that also comes into this equation: who is going to use it? When are they going to use it? Because maybe speed is really, really important, or maybe it's not so important. Maybe things can go slow. So all of these things are really important when we want to make content, when we want to use content, when we want to buy content. And this is a report that Rosa and I contributed to that was published this year, where nearly 300 academics and industry and also public sector in the UK at Leeds sat together, both physically and then after a while online, to look at what kind of principles are important when we want to design content. And so it kind of needs to be driven by learning needs, but you also need to do this rigorous evaluation. Because how do we know that the learning and training we do in VR actually is transferable? I think at the moment, a lot of people just think it is. And maybe they test it on one or two people, or there are some anecdotes around it, but we don't know. And for us as a university, wanting to start to use this technology for really everything, because it solves a lot of issues, a lot of problems, if it works. We also have to be careful in these things. And I think the previous slide really underlined the principle 3 here, that cross-disciplinary collaboration is super important. And then accessibility, and I hope all of you will go and have a look at this, the World Wide Web Consortium for XR Accessibility, which is our first draft. And this is something we're also very interested in, and USNIMERS is working on an EU proposal to be submitted in end of October with regards to ethics, interoperability, and accessibility. So we care. What we're going to talk about in the beginning today, Ellen and I, is related to eyes and vision in VR. And the issue that is really important is because that the technology, the VR and XR technology today, the principle for simulating 3D is actually really old. It's from 1838. And this has a major problem, which is termed the divergence accommodation conflict. There are people, of course, industries working on finding better ways of simulating 3D, but this is where we are. And I think that for the next 10 to 15, maybe 20 years, for schools, for universities, for industry, technology that we're going to use is going to still be based on this principle. So, I hope you will enjoy today, and thank you for being here.
Thank you, Rigmor. We will now introduce our next speaker, which is Associate Professor Ellen Svarverud from the Faculty of Health and Social Sciences.
Thank you. Good morning, everyone. It's good to see you. I will start with this session with Rigmor will take over after a while. We're going to talk about opportunities and limitations in XR related to what we see, vision and eyes. So we are doing quite a few XR projects now related to eye and vision. And we're working on content design in terms of accessibility, visuomotor demand and perceptual decision making. We're also working on acute and long-term effects on visuomotor function, visual performance and perceptual decision making. And we're trying to understand the impact of usage on eye development. So I'm going to talk a little bit about vision. We're going to introduce, I see many of my colleagues here, so for you this will be very, very familiar, but there are also some who may not know so much about stereopsis, so how we see 3D in stereo vision, but also how we simulate 3D in a virtual display, and what makes XR feel real. So let's start with stereopsis. So stereo vision is sort of the most, I would say, almost say important way of seeing 3D, because this is how we can actually see real 3 dimensions. And we do have stereo because we have 2 eyes, and these 2 eyes are set around 6 or 6.5 centimeters apart from each other. And we do produce slightly different images from each eye. So if you look at this figure at the right here, let's imagine that we're looking at a cube that's placed in front of us, a little bit below eye height. And because we have our eyes on different sides of this cube now, if it's straight ahead, we will see the cube a little bit from the left eye, from the left side, and in the right eye from the right side. And this slightly different image is produced as a stereo image, a fused image by the brain. So this is possible because we have these 2 eyes and they're set in front. And it means that this is a head looked from above. It means that from the left eye we see the left side of the visual field, but we also see a little bit to the right. And it's some restriction with facial features. And it's the same for the right eye. So there's a field in the middle here, which is an overlapping field, and which we can use with both eyes and see stereoscopically. So when we look at an object, so I will just explain this figure first. So this is, well, maybe it's me. You can think that you're looking from above through my head and at my eyes from the top. And I'm looking at an object here. And when I'm looking at an object, I have to point my eyes exactly to that object to see it clearly and single. So this object is now projected onto the back of my eye to a place in the eye called the fovea, which I've just given. Yeah, I've almost said something very rude now, but so I labeled it F. So when this object kind of is projected exactly on this area in both eyes, we will see this object single and clear. So let's introduce another object, and we're putting it a little bit further away. So this blue object here now we're still looking at the red object, the closer object. The blue object now is projected also on the back of the eye, but in a slightly different position. And you see that this position is a little bit different in the two eyes, and this is called the retinal disparity. And this is why we see two slightly different images. And when the brain gets information from the eyes about this particular constellation, the brain will interpret this as something looking a little bit further away than the object I'm looking at. If I now change focus and look at the blue one, then my brain will interpret the red one as being closer. So now we just talked about, so this is the basics in the eyes, but I will also say a little bit about the brain, because we are very good at discriminating differences in depth if we have the right, if everything is right in our visual system. But it means that we need to have a proper vergence control. So Rigmor talked about the vergence accommodation conflict, so we'll come back to that. But vergence is pointing your eyes to the object you want to look at. And you need to be precise at doing that. So that means that your eyes the muscles controlling your eyes need to be able to work together. But you also need to have a fully developed central part of the eye. If not, then the brain cannot interpret the image. And of course, the brain needs to understand that these two images need to be fused, but the brain need also be fully developed from childhood. So let's look at a little bit more what's going on. So this is also the top of the head, right and left eyes. And what is happening is that seeing stereoscopically is a it's a very complex process. But the image hits the back of the eye, and the left side of the visual field will reach the right side in each eye and will be sent back to the brain and in the area just behind here, behind your back of your skull. And the same will happen for the left side of the field. And now I confused you again. Sorry about that. The left side of the field will end up in the right side of the brain. The right side of the field will end up in the left side of the brain. Sorry about that. And this is the first time actually this information meets. So it's a long way through the whole brain to actually get this information. But it doesn't end here, because in the brain, this is a monkey brain, so but it looks quite similar to a human brain. So we have our eyes here, and the first visual information center is back here, which is this place here. And all those little dots here, or blobs, they are parts of the brain that actually process information about stereo. So it's complex. So stereo is an important part of understanding 3D. So let's look at how this is transferred into a 3D display. So when we want to simulate a physical 3D environment, we typically give, depending on what kind of display we have, but we typically give one image to each eye, and these are slightly different. And when you make this slightly different, then you create a stereo image. In this display, you also produce content that are on certain distances. So if you want an object to be really close, like 40 centimeters, then you produce the information so that we have to converge and look at that object at 40 centimeters. That's called vergence. That's pointing towards an object. In a 3D display, virtual display, there is also some 3D from motion. And you know this, that objects that are very far away, they move very little if you move, and objects are very close to us, they move a lot. And that is also transferred into virtual displays. And there are also many cues to depth, which we're using all the time. I'll come back a little bit to that. And these displays, they can produce and simulate objects at any distance, so near, far, whatever. And both the stereo display and the where we have to look to see an object, so if it's close or far, that is also possible to simulate similar to the real world. What we cannot simulate with today's technology, which is the same as we saw 1838, is where we focus. because that's depending on where we have our screen. So if you have a screen at 40 centimeter, then we have to focus at 40 centimeter. If we have it at 2 meters, which is very typical for head-mounted displays, then we have to focus at 2 meters. But we can still produce content at different distances. So I'll explain that a little bit further. So, so we're now back to the physical world. And these are my eyes again, looking at an object. And when I look at an object, I point my eyes to that object and I focus at that object. And there's a close neurological link that says that if you are looking closer with your eyes, pointing your eyes close to an object, you will also focus at that point. If you put an object closer, you will change. You will point your eyes closer, you will also focus closer. And this is neurological link. You can't really disentangle those. But in a physical world. But we do that in 3D displays all the time. And so this is, I will try to explain. So let's imagine that the green plane here is the digital display. So the head-mounted display or a 3D screen or whatever. And let's say that we want the person to look at something that is a little bit farther away. Then we're asking this person basically to say, focus at this distance, but point your eyes towards this distance. And what you're asking this person now is to break the neurological link. If you then move the object closer, you still have to change where you point, but you still ask them to look closer. And if you're putting something really close, you're doing the same. You ask them to focus here, but you ask them to put their eyes here. And this is one of the really big things, vision-wise, in 3D virtual displays, is this a problem? We say it's a problem, we think it's a problem, but we don't really know. So that is really interesting. So this is a figure showing the physical world. So here this person is looking in the middle of the corner, and these kind of bluish shadows is where they focus. So they're focusing and pointing their eyes to the corner. And then it will look clear and single in the corner, but things that are closer will look a little bit blurry. If you use a digital virtual 3D display, you have to focus at the display screen, but you can still point your eyes at a different location. The result here is that you always will see the clarity of the scene will look the same, independent of where you look in the scene. But you still have to point your eyes at different locations. So, what makes XR feel real? And XR feels real if it's close to our expectation of the physical world, like Rigmor was introducing. Maybe it's a little bit different for different tasks. Not maybe, it is different. But what is important is that we're using cues around us. We're using this information and we're combining it in the real world, or physical world, to make sense. So that we can understand the physical space, but also interact with it. So these are some examples. So this young lady, she already understands the shape of this drink bottle. She understands how big it is, approximately. She understands the texture of it. She looks at it and then she thinks, this has a certain texture, because she can see some shadow, she can see some lighting. And she can pick it up and she can drink. It's a quite advanced task, but she can do it quite early. He uses other cues to pick up this ball that comes very fast towards him. He's quite excited. When we do skiing and sort of something fast, we have to use our visual cues to understand how we can do this without falling or hitting someone, or sometimes we fail, but we're using our visual system extremely efficiently for that. And we break a glass, then we understand, we can look at this and you do understand it's sharp, you can see it. It's a translucent object, but you can still see it and you do understand the shape of it. And all these are made from cues that makes us understand the physical world. And we have to transform that into the virtual reality situation. And I do understand how to get to Paris. I can close my eyes and I can picture myself going out of this room. I can go out of the building. I can walk to the train station. I can imagine how to get to Paris without actually seeing Paris. And I do want to go now, actually. So, but in our natural scenes, we have all these cues available to us. And, you know, we don't really think about them. We have perspective, we have shadows, we have overlay, overlap. We have all these cues and we use them all the time and we combine them. And if some cues are missing, we just use some other cues instead. We will always use what we have available, and the more cues we have, the better we are at judging and understanding locations. So many of you may be familiar with the Ames room. And you can look at this and you can think, yeah, there's a small girl and a large girl. And we just think that. Most of you would just think, yeah, small and large. And then you don't even consider the point that they are clearly not. That cannot be possible. You just don't have a girl this size and a girl that size. But we're quite happy to just say small and big. And the reason why we do that is that there have been some cues taken away from us here. So we're using the cues we have. And size, familiar size, is such a strong cue. And there's another strong cue here, and that is texture. And I'm going to explain to you. So this room is, in reality, is very, very tall and far away in the left corner. So that's a very, very tall wall. And all the texture elements here are scaled so that they're bigger further away. And the window here is bigger than on the right side. So this means that we are just fooled. And the reason we're fooled in an image like this is that 2D, we're taking away some cues. And one cue that's taken away from us is stereo vision. So if you can do this in a physical room too. You can look into this with one eye. And because you just have one eye, you don't see that this is happening. If you were able to use two eyes, you see it immediately. If you were able to move from side to side, you will see that this room is something is funny going on. And we've been doing this doing experiments on this, and created a virtual Ames room. And I will try to explain very quickly. So this room has a very strong texture element, and we can expand and contract it around the participant who's wearing a head-mounted display. So that there's binocular vision, there is stereo vision, and participants are allowed to move. But because it's always the same amount of tiles and bricks, and they're just scaled. So if we scale the room 4 times the size, then these bricks will be 4 times the size. So the people stand in this room and they have all the cues. They're allowed to move, they can use their stereo vision, they can do anything, and they don't see the room change. And this is about expectations. They don't expect it to change. We also see that if we present objects in rooms like this, and we ask them about distances, they will be heavily affected by where we put the objects. So this we have done to try to understand how vision function, but we also use things like this to understand, go the other way. So this is more about the brain, but we're now doing experiments where we look at what happens to the visual system. So a very recent paper now is saying that it's likely to believe that the most reliable of the available cues will, this ability to use the most reliable cue will also extend into digital overlays when the real and virtual worlds coexist. So, which is a situation like this where you saw Walter showing you yesterday. So what is happening here, that this is a virtual object with an accommodation divergence conflict. You're asked to focus at 2 meters, but you're asked to converge at 50 centimeters. And you're also looking at an object at distance. So there's a lot of things going on. But the question is, what happens if you ask people to do a task like this? Will it impact on the visual system? And Walter showed you yesterday that it does. And we're early days, so we don't quite know. But I will... Oh, no, we don't want to do that. So it takes too long. I want to do it, but I can't. So this is just an example how visual performance actually may change after doing such a task where people have to really concentrate. So sorry, Walter was explaining it yesterday, but I think it's so good, so I will do it again. So we use an instrument where we can see where people look and how they focus. So what we see is that when we show a distant object, and we let people look at 40 centimeters and then move to 4 meters and look back and forth. And what we see is they're very good at looking precisely where we want when they look at distance. And they're quite good when they look at near. This is just an example, so maybe not behavior for everyone, but in this particular person. Good at looking at near. And then do this task for something like 20 to 30 minutes, and then we do this again. And now we're basically breaking their accommodation-vergence relationship. And I think that is exactly what we're seeing in these graphs, is something has happened. Because now the person focuses nicely on distance, but cannot change focus to near. And this is very exciting, and we are just, we're very excited about it. And I could go on this, but I think this is about perceptual decision making. I will hand you over to Rigmor, who is going to talk more about that.
So, thank you, Ellen. So actions in the physical world very much rely on perception for decision-making and task performance. In particular, if we are doing tasks that are related to learning or training or doing something, manufacturing job, or what it is. These things are important. So Ellen has talked about stereo vision, which of course is an important factor into this. But of course, we also need to have eyes that can perceive details and perceive color in combination with stereo. And as Ellen said, this is all related to both how the eyes are developed and function. And to have stereo, you have to have two equally good eyes. But it's also, of course, dependent on the brain, because we see with the brain. When it comes to perceptual decision-making, one of the most important bits we're doing, that is to detect when there is perceptual uncertainty, when we're not sure about what it is. And this requires quite a lot of attentional resources to make sure that we're processing a task accurately. I'm going to speed, because I don't have a lot of time, right? So we can talk about things afterwards if there are things that I've sped too fast. But this is the most important thing, that we actually take time and we can see and decide when we're uncertain and check it again. The other things we know is that for decision making, when you rely on visual information, we know that you are best in making decisions, and that means when you're best, it means speed and efficiency and quality. And that is when we have scenes that have intermediate complexity. So I'm back to this, how real does it really have to be in VR? And the other thing is that scene content predominantly is conveyed with high spatial frequency information. So that's edges, basically, for improving decision making. So the other factor that comes into this, of course, is sensory motor control, the interaction between what you see and what you do. Because your eyes, when you have vision, even if you have only vision with one eye, drives how you move your body and how you do things. And for a lot of tasks that at least we want to train people in, and I know the industry here in Kongsberg want to train people in, and the astronauts and the surgeons, it very much relies on eye-hand interaction, and that this sensory motor control is working properly. And when that's working properly, you have good perceptual decision-making. So here I've taken some of our favorite things in Norway, Magnus Carlsen and chess, and here he plays with Caruana. And how Caruana shape, select, revise and sequence hand and finger movements to reach a visual target. And in this case, I'm going to go back and forth, it's the night. That really relies on the lowest movement-related cost in his neurological system based on active vision, how he uses his eyes and the visual information. And that's very much down to eye movements and looking and focusing, which is accommodation and convergence. Looking somewhere and focusing on it, so it's single and it's clear. And then, of course, in any situation, not only Caruana playing against Magnus, it's the expected consequence of the action. Do you win or do you lose? So this interaction is really, really important. And when we then talk about perceptual uncertainty, in this case, and for many situations, speed and accuracy of picking up an object, here like the night, it really relies on the degree of coordination between, in this case, Caruana's two eyes. Caruana wears glasses. I don't know whether he sees equally well on both eyes, but he might have trained himself really well to do this. But we are back to perceptual uncertainty, because perceptual uncertainty also has to do how much information do you get. And if Caruana only uses one eye, it takes him longer time to do this task. And there's more perceptual uncertainty when he is to decide how is he going to move his hand to pick up that object. Maybe in chess, speed and accuracy of picking up that object isn't so essential, but in many, many tasks that we're doing when we're training people or they're learning a skill, it might be very important. So that takes us to XR, because actions you do in XR also rely on perception for decision-making and task performance. But the problem is that there is more perceptual uncertainty. And there's even more so if you have eye and vision problems. Light, shadows, contrast, spatial details, color, movement, and 3D, and how this is simulated, and how much of it there is, plays an important role. So also knowing what information not to replicate in content, because it's not important for what we're doing, is also very important to reduce perceptual uncertainty when you work in XR. And then, of course, we are all very interested in using auxiliary devices with our XR technology. But in some headsets now, you get your hand represented. But that representation of how you use your hand and fingers in XR, if it's not accurate haptics associated with it, might also affect uncertainty. And this is important not only for adults in a particular manufacturing job. It's really important when we want to do these things in children. Because there are so many factors affecting how this will go, but also how do they learn things, and how and in what way is it transferable to real life. And this very recent paper that Ellen referred to, they also show that individuals who have even mild binocular vision problems, they are less precise in judging spatial information in XR than those who have normally working binocular vision. Mild problems. A lot of us have that. So I mentioned for you earlier, common people have common eye problems. And we have to think about that. Maybe some of you don't think that Kate Moss is a common person. I think she is. Kate, she has only one good eye. She squints. So she has no stereo acuity. You put her into a headset and she will only see what's presented to one eye. All simulations that are made for 3D, she will not see. She will not get that information. But she's pretty happy putting a VR headset on because she won't have any problems with accommodation convergence conflict. So if you don't know anything about the people you put into the headset, you have no idea whether she can see things or not because she's happy in a headset. This is James, and he has a very good video on Europe, and it was even on New York Times in July. James has 2 good eyes, but they do not cooperate. So he also squints, but he sees with one eye at a time. So he has no binocular vision and no stereo acuity. It's a very funny video. But this is really common. 5% of the population do not have stereopsis, cannot see 3D. But you will not know what they do in your headset if you don't know anything about them from before. 10 to 15% have what we call vulnerable binocular vision. We are not quite sure how they will do in a headset. Some of them might actually do well, and others will have problems. And this depends on the combination of things. And then, depending on where you are from in the world, 40 to 90% need spectacles to see well with both eyes, and they need that correction inside their headset. This is a map showing how prevalence of refractive errors actually varies around the world. But this also means usually that, like in Norway, we have people from all of these countries living in Kongsberg, living where you're living. So you have to think about this and ensure that people are okay. Because if you have these kind of problems, and there are large inter-individual differences in both in color and spatial vision and refractive errors and binocular status, and this will affect to what degree people have stamina when you put them in exile, depending on how you have developed your content. And these are one of the things that we're really interested in. How can you develop content to ensure that people feel immersed? Because we know this feeling of immersion is really important for learning. But as I said earlier, there are technical limitations. Cybersickness is still out there, regardless of what we heard yesterday. But perhaps if you do, like he said yesterday, that you actually do a major operation with your hands, with a real object, that actually might help you in taking down the cybersickness feeling. One of the major issues with cybersickness is very simple. It's to do with interpupillary distance, because the headset cannot make the adjustments for the large variation in differences between these two eyes. Because the optics, when you look through things, the lenses in the VR headset, it needs to be centered on your pupil, on your eye. And for example, the Oculus Quest, that has a range from 58 to 68. But I have a near IPD on 58, so I'm just borderline when we're doing things near. I'm an adult female. A child or a girl, their IPD is between 40 and 50. It's way too narrow. So when we read in the paper that they tested out mathematics in VR in a school in Inlandet on 5th graders, 11-year-olds, and then they said, all the boys thought it was so fun. All the girls puked. Well, we have smaller heads. It doesn't mean we're less intelligent. And we have smaller distance between our eyes. And when the headset can't accommodate for that, it's really uncomfortable. But it's really simple too, right? So this is, what you're doing, when you're doing, what headsets you're choosing, these kind of things are really important. So the cybersickness and gender issues, a big part of that just has to do with headsets being designed for a perfect white 25-year-old male. And so many of us are not that. But form factor is a huge issue too with adoption as we go forward, because going around like this, I don't perceive that we will do. Here are some newer designs that are more attractive. But of course, the major goal is to get VR glasses that looks like normal glasses in the first instance. But of course, the wet dream is to not have anything on your head, to have proper holographics. that we can walk around, that we can be inside without any tools. But the technology, we can't do it. But of course, we dream about that. We heard from Signe Vivo yesterday that they use VR in some situation with great success. It doesn't mean that they experience the things that you and I might experience, but it's still useful for them. But the other thing with XR technology is that there's a lot of technology now that can be used instead of visual stuff. And you can reverse things. So these touching masterpieces, they use actually haptic VR. There's nothing visual, but they've scanned sculptures, and then they've transformed that back to haptic. So when you put your gloves on, you can feel the shape of a sculpture. So a person who's blind can feel the sculptures. That's also 3D perception. And it's an important aspect of how to make things accessible. When can we do things like that if a child doesn't have 3D perception and he needs to learn something? This is not something we can do in manufacturing, of course, but you have to be open-minded and think about all the possibilities that might be there when we move forward. Yeah. So these are some of the aspects we're doing. And when we work in US and IMERS, you've met a lot of the people there. Fantastic PhD students that we have. We are so proud of them. But for us who work on eye and vision, we also rely on some basic science coming in from the sites. And we have two larger projects and labs working on understanding color and spatial vision and how the eye grows and develops. And also, we're working with a big study with schools, following longitudinal study on children to see on how eyes develop, but also how sensory motor interaction is, what's normal, and the link between what's normal and good and efficient with what eye and vision is. So there's a lot of people working on things that are really important for utilization of XR technology in our department. Thank you.